this next example, we're going to look at a situation where the composition is described in an unusual way. We also, in this example, will have another mixing point as well as a split point. So here we have 100 kilograms of a wet material that's to be dried from a moisture content of 0.15 kilograms of water per total kilogram to 0.07 kilograms of water per kilogram total. We want to know how much water is going to be removed, and we want to know how much dry air is in the fresh air feed and how much dry air is recycled. Now, this is somewhat complicated by the fact that the air comes in with some water in it. Typical air contains a little bit of water vapor, right? We usually talk about that as humidity, and later in the course we'll actually learn some other ways of defining this humidity. But for now, as given in this drawing here, we have 100 kilograms of wet material coming in and dried material, which I've labeled as P, coming out. We have air fed to the system, which is F, but it contains 0.01 kilograms of water per kilogram of dry air. Now, F is not dry air, F is moist air. So this is not a mass fraction. Coming into the dryer, well, we'll mix this fresh feed with some recycled air and then send to the dryer A kilograms of air, which will contain 0.03 kilograms of water per kilogram of dry air. Now the dryer is going to remove some of the water from the material, so it will come out with less moisture content in the solid material P, but that will mean more water content in the air B. This is going to be split so that some of it will actually leave the dryer in stream E, and some of it will be recycled back in stream R. Now they say that the recycled air contains 0.1 kilogram of water per kilogram dry air. Again, this is not a mass fraction. So let's look at how we could set up this problem. Okay, so we have here, the streams are the wet material, P the product for the dry material, F the feed, A what goes into the dryer, B comes straight out of the dryer, E is the exiting air, and R the recycle stream. I have water, dry air, and dry material, and I've set these up so that they would be in mass fractions, and I have a total mass of kilograms in each of these. And based on this information, I have the total mass in the wet material is 100 kilograms. And it comes in with dry material and water at 0.15 kilograms of water per kilogram. So the water is 0.15 and the dry material is 0.85, and there is no air in this stream. We know that it's going to exit in stream P. I don't know a flow rate there, so just P amount of this will leave, and it's going to contain 0.07 kilograms of water per kilogram. Again, no air. 0.93 mass fraction will be the dried material. Now the air is going to enter with a stream flow rate of F. It's going to contain no solids, but it will contain air and water. Unfortunately, this is not a mass fraction. It's not kilograms of water per kilogram total, it's per kilogram of dry air. So I end up with not actually knowing this or this. For A, I have a similar situation. I do not know the mass fraction of either of those. I know it does not contain solids, and the flow rate is A. Similarly, B, E, I know nothing on that one. And the recycle stream, I know this thing that somehow is similar to a mass fraction, but not quite. So I have that. So I have an awful lot of unknowns, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 unknowns in this problem. And that's sort of overwhelming. But the real reason I've got so many problems is because of these crazy, not quite mass fractions. So let's try using those process specs, those not quite mass fractions now. So let's just look at stream F. Stream F contains 0.01 kilograms of water per kilogram of dry air. We want to convert this over to a mass fraction. So if we assume that there's 1 kilogram of dry air, okay, so it's sort of like a basis, right? This is a basis for our calculations. Then for that 1 kilogram of dry air, there's 0.01 kilograms of water. That means that the total in the stream is the sum of those 1.01 kilograms. And so the mass fraction is 0.01 over 1.01 for the water and 1 over 1.01 for the air. I could do this same process for all of them. This is going to be for stream A, which contains 0.03 kilograms of water per kilogram of dry air. It's going to have a mass fraction for water of 0.03 over 1.03. For stream R, we have 0.1 kilograms of water per kilogram of dry air. So the mass fraction of water in stream R is 0.1 over 1.1 kilograms of water per kilogram total. Now, if I use these, this is going to clean up that material balance table a lot. So, again, we'll just go through this again. I have 0.15, 0, and 0.85, and 100. That has not changed. 0.07, 0, 0.93, and P. Again, that has not changed. But now then, I know that in all these streams, first of all, I have no dry material. I don't know the flow rates. Using these mass fractions isn't going to change that. But I do know how to write a mass fraction for all of these others. So this is 0.01 over 1.01. This is 0. It really isn't 0. Okay, it's 1.00 over 1.01. This is 0.03 over 1.03 and 1.00 over 1.03. I do not know this. 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 But I do know for R that this is 0.1 over 1.1 and 1.0 over 1.1. So now I have many fewer unknowns, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 unknowns. Okay? I was able to really drop that number by a lot. And in a few moments we'll see that I can also make one more rational reading of the problem statement to come up with another simplification. Maybe you've already seen that. So let's now look at what I have for my degrees of freedom table. So in the degrees of freedom table, I can do the dryer. I have a mixing point, I have a split point, and I have the overall system. For the dryer itself, the streams that are coming in are the fresh feed, I'm going to label that W for wet material, and stream A, and leaving are streams B and P. In that case, the variables I have for those, and you may need to go back and refer to the other table, but I have the flow rates of A, B, and P, and I have the composition of stream B. So I have 5 variables. So it's XB, YB, A, B, P. I can do 3 material balances: water, air, and solids, or the material as we've called it. I get one sum of X equation, and I have used my process specs to write the mass fractions in the streams where the water content was defined. And so based on this, I have 1 degree of freedom at the dryer. If I were to look at the mixing point, I have F comes in, R and A come, or F and R come in, and A exits. Okay, so in this case, all of the compositions are known. I just simply have the variables F, A, and R, the flow rates. I have 3 variables. Now, how many material balances can I write? I have 3 components in the system, but at this point, I only have water and air. So therefore, I can only write 2 material balances. I have no compositions, so I get no help with sum of X equations. I have no process specs. I've already used those. And so I have 1 degree of freedom. How about, I'm going to skip over the split point. Let's do the overall next. So on the overall, the recycle stream is completely contained. I have the wet material and the feed come in, and I have E and P leave. Okay, so my variables at this stage, well, I know the flow rate of the wet material, but I don't know the flow rate of F, P, or E, and I need the composition of stream E. So therefore I have 5 variables. I can do a total of 3 material balances because all components are involved in the overall system. I get 1 sum of X equation, no process specs, and again I have 1 degree of freedom. So let's look at the split point. Now if you just blindly start in on the split point, then I have stream B enters and streams R and E leave. Okay, my unknowns, of course, all of those flow rates and the compositions of stream B and stream E. So this looks like I have 1, 2, 3, 4, 5, 6, 7 variables. I only have 2 components involved here, air and water. I get 2 sum of X equations, no process specs, and I have a degree of freedom of 3. But wait, okay, this is why I saved this. At a split point, the compositions are the same everywhere. That means that actually I do know some of those compositions, okay? In fact, if I know the composition in this stream, stream R, I also know the composition in streams B and E. So these are, in fact, are not unknown. In fact, I only have 3 variables, B, R, and E. I have 2 material balances. I do not have any sum of X equations. And again, I'm going to have 1 degree of freedom. So where do I want to start? They all have 1 degree of freedom. Well, you can kind of choose any place that you would like to. I started with the overall system, so I did this one first, and then I went to the mixing point next. And then I'll follow up with these others as needed. Okay? Main reason, usually I find that sort of is an easier way to solve the problem. The overall system tends to give a lot of good information, and mixing points, especially where they're well defined like this one, are also going to be very useful. So this is based on experience, but any of these you can start in any order, it doesn't matter. So I'm choosing the overall, then the mixing point, and then I'll go to the dryer and the split point next. All right, so for my overall system, well, my overall system, I have feed plus 100 kilograms of wet material is equal to the amount that exits in the air plus my product. Okay, if I do and this is my overall total, I'll write total. Okay, if I do an air balance, I'm going to find that 0.01, that would not be the air, would it? Okay, air 1.00 over 1.01 times F comes in with the air feed. Nothing comes in with the wet material, leaving with the exit of the other 1.00 over 1.10 times E plus 0 air leaves with the product stream. Okay, if I look at the water, 0.01 over 1.01 times F plus 0.15 times 100 is equal to 0.10 over 1.10 times F plus 0.07 times product. And that was an E, not an F right here. Okay. There, that was a little hard to read. Okay, so got my material balances there. So I have the unknowns F, E, and P. I have 3 equations that have only those 3 unknowns. I could also write the balance on the solid material. Okay, and I need to solve these. Now, this isn't really that bad. I can solve this directly for P. I can solve for P is 91.4 kilograms of product. And if I know P, then I've got equations with F and E in them. Okay, so this is my little re-sketch of the mixing point, okay? So this is the information that I have at this point, and I can write various balances. So if I wanted to do a total mass balance at the mixing point, I have 96.5 equals R plus A. And if I were to do an air balance, I end up with 1 over 1.01 times 96.5 is equal to 1 over 1.1 times R plus 1 over 1.03 times A. And a water balance is 0.01 over 1.01 times 96.5 equals 0.1 over 1.1 R plus 0.03 over 1.03 A. Okay, so I can solve any two of these, okay, as a system and check in the other. I find that R is equal to 30.0 kilograms is recycled, and A is 126.5 kilograms is fed to the dryer. Now I could go on and look at other pieces if I wanted to know other things, but at this stage I am ready to answer the questions. So, how much water is removed? Well, okay. So the amount of water removed, I started off with 0.15 times 100, and when it left, that's a minus sign, 0.07 times 91.4 kilograms left. So therefore 8.6 kilograms of water were removed. Right? The amount that came in minus the amount that left in the product tells me how much water was removed. They ask how much dry air in the fresh feed? Okay, well, what's my mass fraction in air in the dry feed? Well, it's 1 out of 1.01 times the flow rate, 96.5. And so therefore 95.5 kilograms of dry air are fed. And how much dry air in the recycle? Well, I know the amount in the recycle stream and I know that composition. So 1 over 1.1 times 30, 27.3 kilograms of dry air are recycled. So at this point we have now successfully solved two problems with mixing points and split points and multiple units, and we're now ready to move on to the next lessons where we'll begin looking at reactions.